Good day to you all. I am Bart Frankai, a third-year PhD student at the Sapienza University of Rome in machine learning. In this talk, I will walk you through some of the challenges and solutions that we had to the prediction of daily coronavirus cases via deep sequential networks. As anticipated, our objective is to predict the daily viral spread of the novel coronavirus pandemic, and an immense amount of researchers in the epidemiology and virology has studied infection spreading by using stochastic models. Generally, virus spreading can be measured, and these measurements can be plotted in time, thus generating a temporal disease trajectory. The virus time series have a lot of characteristics, among whom the most important are the measurements are done regularly. In the case of coronavirus, the measurements are done daily or at most weekly. The time series spans over a long period of time until the virus has finished spreading in the population. We all know that the coronavirus pandemic is still ongoing, but at the moment of this study, the pandemic had reached the second wave of infection, circa autumn 2020. The measurements within the temporal sequence have latent dependencies that can stretch over long periods of time. As demonstrated, the coronavirus's effects are usually only noticeable after 2 or 3 weeks of the virus incubation. Considering what we said until now, this paper and this presentation analyzes the effect of the mobility containment policies imposed by governments worldwide on the spread of the pandemic. And additionally, we want to predict daily positive cases based on the infection time series. The literature of the epidemic spread prediction can be divided into two classes, such as diffusion models and time-related models. Diffusion models are based on specific infection parameters of the virus under consideration possibly of augmented data, such as environmental data based on traffic and weather data, and of course social data. Models based on time series, among which stationary linear stochastic models such as ARMA and ARIMA, where the epidemic spread at time t is predicted by regressing its past values. When multiple time series are involved in the prediction, VAR models have been used, are the most used family of multivariate predictors, but we want to concentrate more on deep sequential models such as long short-term memories, which are a subfamily of recurrent neural networks that, contrary to the VAR, so stochastic models like VAR, learn long-term patterns in sequential data. These methods have been successfully used in many sequential applications, such as machine translation, speech recognition, risk prediction, and many others, but only lately they have been applied in the field of epidemic prediction. To summarize, available studies confirm that diffusion models are highly sensitive to epidemiological parameters, mainly the infectivity period and the incubation period, making them less effective when these parameters show a high variability within the population, as for COVID-19. Stochastic models instead may rely on observable data, such as the daily infections, meteorological, and traffic data. However, they are less effective with long historical data. This is critical since the spread of the infections for COVID-19 has been highly dependent on national mobility containment and other policies to combat the disease, whose effect can only be observed after several days or weeks. To conclude, deep sequential models appear to be more promising for predicting the COVID epidemic. They do not need to explicitly encode epidemiological parameters and have been shown to detect underlying characteristics and long-term dependencies in the data. Trajectories like COVID-19 infection spreading in a population are strictly dependent on time. The number of infected, recovered, and deceased patients are measured according to specific time intervals. For example, most countries perform tests and update their metrics every day. Hence, the literature models time-related information with time series, and we consider only time series, discrete time series in this study, where we assume that time series is an ordered sequence of events or random variables, x happening at time t, over a discrete set of timestamps t. Now, to formalize, let M be a time matrix of T rows and F columns, where F represents the set of random variables, or in machine learning jargon, features. And the figure here on the left of the slide represents this formalization, where each cell, xt and x of tj, is a jth feature recorded time t. Now, additionally, in the coronavirus and generally in the multivariate scenario, we need to adopt the notion of time lag that considers random variables of the same kind from the past to make predictions in the future, which we name with lead. We denote with k the number of days to look back, so the lag, and with L the number of days to predict forward in the future. Hence, we need to extend the formalization of the time matrix M depicted in the previous slide into time tensor N of T, K, and F that considers the lag concept of the temporal sequences. The selected matrix N of T from N, from the time tensor N, is populated with all the features in F that happened at most K time steps before the current time T. Not that we need also to take care of negative time steps, and that's why we have the if condition in the equation down below. Now, to clarify the tensor structure, we transform the first dimension into a hash table whose elements point to a K times F matrix. Assume that each hash table element represents a timestamp ranging from T1 to T3. Note that we populate each matrix according to the equation in the previous slide. Because K is equal to 3, so the lag is equal to 3, the first two rows of the matrix corresponding to timestamp T1 are equal to -1, therefore the else condition in the previous equation. This happens because there are no events previous to time T1. The last row, however, contains the feature values that occur at time T1. Similarly, T3 points to a matrix that considers all events happening from T1 to T3, and we can apply the same reasoning for time step T2 with lags K equal to 3. The literature has not exploited the temporal and spatial dependencies of the coronavirus infection curves in conjunction. So recent research on the prediction of positive cases due to the pandemic concentrates only on temporal features. To address this gap, we propose CoRoNNa, CNN, a conjunction of CNN and RNNs, which is a predictive framework that handles a mixture of temporal and spatial characteristics of the multivariate coronavirus trajectories. Our framework consists of 3 main blocks configured independently from one another: XCNN, which is a convolution of the input trajectory at time t; HCNN, which is a convolution on the hidden vector at time t-1; and the main RNN blocks, which find the features of the curves of daily infected patients. Now, we need to actually assess why this conjunction of spatial and temporal features is beneficial, and that's why we have proposed this framework, which distinguishes itself from other predictive models proposed in the literature because it can adopt heterogeneous CNNs for the hidden vector and the input. So these two blocks can be configured separately from one another. Researchers also can employ different architectures and hyperparameters for the CNN blocks. For instance, it is possible to use pre-trained models and apply transfer learning techniques to model the input and the hidden vectors. Similarly, we can extend the RNN component with LSTMs or groove cells. Moreover, our framework is polymorphic and agile, where future researchers can rely on the proposed scheme of the network as a plug-in, plug-out module where the components are configured according to specific requirements of the problem or the task at hand. This figure depicts the unrolled structure of our framework. The architecture is similar to a classic RNN with the addition of the ad hoc configured convolutional modules. As in a simple RNN, at each time step t, we apply two convolutional operations, in other words, HCNN and XCNN, on the previous hidden state HT minus 1. Taking into consideration that RNNs suffer from problems such as the vanishing and the exploding gradients, we improved the base structure of the CoRoNNa model by replacing the RNN block with an LSTM block. An LSTM block aids in learning long dependencies on the coronavirus infection trajectories and short spikes due to, for instance, bursted tests or re-emerging cases as per violations of the adopted mobility containment policy imposed by the governments. Since our experimental analysis objective is to study in detail the effect that different mobility containment policies had on the coronavirus diffusion, we consider the following countries: Italy, Brazil, Switzerland, South Korea, Japan, and Texas in the United States, each of whom can be grouped into three categories. Category A, which represents countries adopting severe lockdown policies, B, which represents those countries with light containment policies, and finally C, countries or regions that decided not to impose any constraints, such as Texas and Brazil. There is one country or region more densely populated, such as Italy, Japan, and Texas, and one unevenly populated, such as Switzerland, Brazil, and South Korea. The data sets were built using two groups of features: F1, which takes into consideration COVID spread of infection data, and F2, mobility patterns. We collected the F1 data in Italy from sito del Dipartimento della Protezione Civile, Emergenza Coronavirus, whereas we collected the data for the other countries from our World End data. The provided features comprise a number of daily positive cases, a number of deceased persons, daily swab tests, and ICU admissions. And regarding the F2 mobility patterns, we exported the data sets provided by Google and Apple through their websites. Notice that Brazil misses the feature of number of daily swab tests. The Google data set provides the percentage changes in visits and length of stay in places like grocery stores, transit stations, bus and trains, obviously, parks, workplaces, and residential areas within a certain geographic area. The Apple dataset collects three types of mobility information. In other words, driving, walking, and transit. And to be fair, we removed weekly bias from each time series and reduced anomalies using the moving average methods. We smoothed also each time series by taking the average over a 7-day window. And finally, we normalized all time series in the same range. The considered task is to predict the variable daily positive cases, namely DPC, as a function of the other covariates. The objectives of our experimental analysis are two. The first one is to assess the predictive power of infection and mobility trajectory to forecast COVID-19 viral diffusion in countries that adopted different containment policies. And the second is to compare the quality of prediction of stochastic and deep sequential methods, in particular CoRoNNa, regarding objective number one. Now, for the experimental setup, we used RMSE, so root mean square error, for the metric of evaluation. For the time window, we used a combination of all lags in the set of 3, 5, 7, 10, and leads in the set of 1, 3, 5, 7, 15 to measure heterogeneous metrics and heterogeneous performances of all methods. The training has been done according to a 60-10-30 split into training, validation, test set. So that was how we evaluated our methods. And the splitting is done sequentially in the time axis. So the training instances are consecutive, the validation set instances are consecutive, and so on and so forth. Now, we compare our strategy with Yang et al., denoted as LSTM Yang, one of the most recent and cited works in this area, and with the best known auto-regression algorithm for multivariate series, namely VAR. We do not compare with diffusion models, since first, our focus here is on time series, and second, as already discussed and shown by the experiments in Yang et al., diffusion models are very unstable when epidemiological parameters are highly valuable, as for COVID-19. LSTM Young has been configured as presented in the paper and contains 25 cells. The output layers of both models, so CoRoNNa and LSTM Young, use a sigmoid activation. We use the ADAM optimizer with the default parameters with the mean square error loss function during training, and we train all the parameters, CoRoNNa and LSTM Young, with 300 epochs. Concerning var, we first verify the existence of a relationship among the variable to be predicted and the other time series using the Granger's causality test to disprove the null hypothesis that past values of a time series do not influence the other series. The test confirmed a dependency among DPC and the other series, and next we performed a stationary test with ADF on all features. And one of the main problems with autoregression is that a stationary condition is needed for all considered variables. Since, as expected, some time series turned out to not be stationary, we applied a commonly adopted method, which is the quadratic detrending. However, we have been unable to obtain stationarity for several features. For example, the number of swab tests performed daily, which may hinder the efficiency of VARs in this context. Now, in this figure, we compare the performances of the three considered methods in terms of RMSE. For visualization purposes, we present the scores on a logarithmic scale, and each row of the plots represents a country from the data set ordered by the adopted policies, and each column shows a different lag, K. And notice that while CoRoNNa, LSTM, Young, and Random Forest produce different RMSE scores, when varying the lead L, VAR predicts the entire trend line of the infection curves, hence having the same RMSE for all L. The graphs here lead us to conclude that changes in the mobility data are predictive of the virus spread, while infection data is not sufficient to obtain reliable predictions. The observation supports that the prediction errors are much lower for countries of type A and B, as shown here, where mobility data have changed considerably according to the containment policies issued by the governments. Instead, no countries of type C, for countries of type C, no system can predict the viral spread. In these countries, mobility data have not changed in the considered period. Therefore, DPC predictions relying only on changes on the infection data cannot be made. Finally, we analyze the importance of single features in the mobility data and predicting future cases. We computed the Pearson correlation between the predicted variable DPC at time t and each mobility covariate xi with lags k belonging to t-1, t-2, up to t-29. The result is shown in the heat map histogram on this figure for Italy and Switzerland. We observed that the variable with the highest predictive power for both countries is residential, and the correlation remains very strong with both small and longer lags. Low traffic, in fact, in residential areas means that people stayed at home, and indeed this has been the most effective countermeasure for to contain the coronavirus pandemic spread. The other mobility features have a stronger correlation only at longer lags, almost 3 weeks, and these results confirm the effect of movement containment policies, which has had a positive impact on the infection only after a few weeks. Deep sequential methods are acknowledged to have a higher capability to capture distant relationships. To test this aspect and more closely compare CoRoNNa and LSTM Young, we plot the real-time prediction of the trained models for the infection curves of the two countries, so Italy and Switzerland. Based on the previous figures evidence, we now set L equal to 7 and K equal to 30. The plot in this slide shows that for the two methods, the training, validation, test, and real-time prediction phases, we observe that CoRoNNa closely follows the ongoing second wave of the infection, while LSTM Young follows the real curve only during the first part of the prediction phase. To conclude, diffusion models are less effective at predicting viral spread of infection diseases because epidemiological parameters have different manifestation from individual to individual. So it means that the incubation time might vary from patient to patient. And we have proven that changes in mobility data are good predictors for future infections, because there are stronger correlation with daily positive cases at longer gaps, also at longer lags. And CoRoNNa shows superior ability at capturing long-term dependencies with respect to the literature.